Welcome everybody. So today we're going to be looking at connectives, and the question we're going to be looking at is, are they enough? So far we have 5 connectives that we've used, and they are not, and, or, implies, and if and only if, right? So are they enough? So is it possible that we may want to say something logically that we couldn't say with these connectives? It's an important question to ask. So let's suppose, let's start with an example. Let's suppose we have a new connective that we call sharp, and what it does is takes the majority vote. So this is a sharp, it's a connective among 3 things. So the input is 3 subformulas, and it's gonna give you what the majority of those 3 says. So the sharp of phi, psi, and theta is going to be the valuation applied to this is going to be true if at least 2 of them are true. Okay? And it's going to be false if at least 2 of them are false. Okay, so that's a new connective. I just made it up, but it's a connective. And the question is that, okay, so is it a new connective, or is it something that we have already, because we can use these ones that we have already to build this connective? Is it new? What do you guys think? Well, no, the answer is no. It's not new. We can write this one with the other ones. So this formula, this sharp, is tautologically equivalent to the formula phi and psi, or phi and theta, or theta and psi, right? So at least 2 of them are true. So we don't really need to add a new connective to say this one, because we can say it with the ones that we have so far. Okay, to be able to understand if the question of whether the connectives are enough, or how to ask the question even, we need to start studying these k-place Boolean functions, right there. So what is a k-place Boolean function? So Boolean values are true and false. The t and the f, they're called Boolean values. So these Boolean functions are functions that take an input from tf to the k, and the output is just true or false. Alright, so the input is a k tuple of true or false. So recall, let's do the example of k equals 2, that tf to the 2, so this is a set of pairs of true, false, consists of this set, tf, tt, tf, ft, ff, right? So these are the 4 pairs of true or false, and then you can do the same with triples. You're gonna have 8 combinations, or quadruples, 16 combinations. So these functions, the k-place Boolean function, takes k tuples of true false and outputs just 1 true or false. Okay, so let's consider an example. So let k be a 2-place Boolean function, so a binary Boolean function, given by the following values. So whenever you have a Boolean function, you have to just list the values. There is no way to say. So for instance, ktt equals true, ktf equals false, kft equals false, kff equals false. Okay, then you can define just any function you want, get them by any value. This one in particular, if you pay attention, is just the same as what the AND connective does, right? So it's only true when the input is true, and it's false in the rest. So this function corresponds to the AND connective, and we can have another function for the OR connective, the implies connective. Each connective has a function like this, but actually not just each connective, each well-formed formula alpha that we can write in a sentential logic using, let's say, variables a1 up to ak, is associated to a Boolean function, right? To a k-place Boolean function that we call b sub alpha. And b sub alpha is going to be this k-place Boolean function that goes from k tuples to true and false. For example, the k function that we define right here is the one associated to the formula a1 and a2, right? So a1 and a2 has this k function associated to it. That's b sub a1, a2. It's true only with two true. So what about our connective here, majority vote connective that we have right there? So what would be the Boolean function associated to that one? So for that, we need to write down the truth table for the sharp function. And to define the truth table, what do we need to do? Well, we write down the 8 combinations of true and false, like among all the other variables, like 8 of them. And then the sharp is going to be true only when 2 of them are true, and that's in these 4 cases right here. That's when 2 of them are true, and it's false in the other 4 cases. So that means that the Boolean function associated to this is essentially the one that reads the truth table right there. So that's what it does. So the Boolean function b sub alpha, where alpha is sharp of a1, a2, and a3, is this one up here. So b alpha of TTT, it's going to give you 3. B alpha of TTF is true. B alpha of TFT is true. And so on and so forth. There you go. We call this function b sub alpha the Boolean function realized by alpha. Sometimes we say associated to alpha or realized by alpha. And that n that's on top on the superindex represents the additive, how many inputs it has. In this case, has n inputs, but in the case right up here has k inputs, and then the and has 2 inputs. So that's why we should have put a k and a 2 right there. But we don't need them. If we know what we're working on, sometimes we omit that superindex. Okay? Let us quickly look at another example. So let alpha a more composed example. So let alpha be the formula a1 or a2 altogether implies v3. So what is the Boolean function associated to it? So what we need to do is essentially do the truth table for this formula right here. So for the truth table, what we do, we start with the 8 combinations for a1, a2, a3 right there, and then we want to find the truth table for this whole thing. We need to copy the column for a1 below the a1, and then we need to copy the column for a2 below the column below a2, and copy the column for a3 below a3, and now we go into the connectives. The first connective is the OR. I forgot the parentheses right there, but the connective right here, first we do the OR, is true when one of those is true and false at the end, and then the implication between the when the blue column and a3 column is false only in that situation and that situation, which is when it's true and false, and it's true in all the rest. So this gives us the Boolean function associated to this formula. Oh, and this is also false in that case. And the Boolean function is right there. So you have to look at that column below the implication, and then you get all the values. We're just copying that one, the one that is red and blue, the one that is marked, and we get all the values for the Boolean function. Good. Let's make a couple of quick observations. First, given 2 well-formed formulas, alpha and beta, over the variables a1 up to, let's say, an, we have that alpha is tautologically equivalent to beta, so they are equivalent, if and only if these functions are the same. Alright, so if the functions they realize are the same as functions, that means that for every input that you take, the input is as an n-tuple, when you get the same output. Okay, so the whole functions are the same at each value. So that means that the truth tables give you the same values. So that means that they are tautologically equivalent, right? That's what it meant, that you always get the same values. And then a very quick observation, that alpha is a tautology. If you guys remember what tautology means, is that it's true independently of how you assign the truth to the variables. That's going to be if and only if b sub alpha is the constant function that always gives you true. Okay, I'm just repeating the words essentially in a different way. Good. Okay, so these b sub alphas help us to understand these notions. So let's now go back to the main questions that we had before. Now we can ask the question more formally, now that we have the language to talk about it. And the question now becomes, does every k-place Boolean function have an associated formula or come from a well-formed formula? So if you're given the k-place Boolean function, does it come from a well-formed formula? So in other words, this is exactly what we're asking. So you're given a function f, it's a k-place Boolean function f. Does there exist a well-formed formula alpha on the variables a1 all the way up to ak, such that the function f is the same as the Boolean function associated to alpha? What do you guys think? What should the question be? And it's not an easy question. It's a theorem, and the answer is yes. So the connectives that we have so far are enough to get you all k-place Boolean functions. So let's look at a proof of why this is the case. So we're given such a function f, and what we want to do is to build or find a formula alpha that is gonna realize this function f. Okay, so let's start with a simpler case and then move on to the general case. So suppose first that f is true only on one value v. Okay, so from all the possible v's that belong to tf to the k, suppose you only get true once and all the other ones are false. Okay, so that's a simpler case. Let's find a formula for this. Let's look at an example first and then see how that works in the example. Okay, so suppose we have a function f and the function is the following. It gives the following thing. Here we're going to write down all the values for f. So f is going to have 8 possible inputs, and we're going to tell you what to do in each input. It's going to be true only on that one right there. Only that one is true. All the other ones gives you false. Okay, so only on v equal tff you get true, all the other ones are false. So in this example, let's see if we can write down a formula whose Boolean function is f. So how do we do this? So here it is. Let alpha be a1, not a2, and not a3. Yeah, because we want alpha to be true only on true, false, false, right? So true, false, false is going to correspond to yes a1, no a2, no a3. This one is only true when a1 is true, a2 is false, and a3 is false, right? So that's the formula that we need, and it's going to be false in all the other cases. Let's now look at the general case. Again, the general case under the assumption that we only get one true value and all the other values are false. Okay, so in this case, so we have this value v where the formula is true, all the other ones except for v formula is false. In this case, right, in this example right here, the v corresponded to true, false, false, but there could be some other v. And now it might not be 3, it might be k. Let's look at the general case. So we start defining this this formula beta sub I for each I. So for each I, beta sub I, let's call it as j maybe. Beta sub j is going to be equal to a sub j or equal to not a sub j. This is a variable a sub j, depending whether v is true or false, right? Because if we want, the point is that if v is true at a certain point, we want that variable to appear positively, like in the example right there, and if v is false, we want it to appear negatively, like a2 and a3 right here in the example. So beta I is just variable, maybe with a negation next to it. And then we define alpha, the full formula, to be the conjunction of all these guys. Okay, so now we have exactly like in the example right up there, that's beta 1, that's beta 2, and that's beta 3, and the alpha is the conjunction of all of them together. Okay, so that's the general case. It works always when we assume that f has only one true value. Okay, so let's consider now the more general case when f can have any number of true values. right? And let's say the true values occur at the inputs that we're going to put names, v1, v2, all the way up to v sub l. And these are the inputs, remember, are tuples that belong to true, false to the case. Okay, so for these L tuples, we get that F gives you true. For all the other ones, it's going to give you false. So let's see how we build now the formula. Let's start by looking at an example. This is the example. I'm copy and pasting the same example from before, but now I'm going to change a few of the values. So we change that one, well, that one is flat, and that one. Okay, so now let's suppose we have three values. So v1, v2, and v3. So L equals 3. So those are the three places where it's true. The formula is false. Elsewhere, what do you think our alpha should be? That's something that is true exactly at those three places. Well, we know what to do when it was true in only one place. And we can write alpha 1 equals a1 and a2 and a3. It's only true when a1 and a2 are true and a3 is false. Right, so B alpha 1 is only true at TTF, at exactly V1, right? And then we can write, for V2, we can write another formula that is, whose associated Boolean function is true only at V2, true, false, false. And we can write another Boolean formula, alpha sub 3, which is only true at V sub 3. V alpha 3 is only true at false, false, true. That's V sub 3. Okay, so now we have these three formulas, but now we want to put them all together. We want one that is true exactly at the three places. So what do we do now? So now we just take the disjunction of these three formulas. We get alpha 1 or alpha 2 or alpha 3. So we put them together with ORs, and now we get something that is true exactly if one of these three, in each of these three places, alpha 1, alpha 2, or alpha 3 is true in those cases. And then all the other cases, we get false. Okay, let's now look at the general case. So the same as before. Now suppose, again, like we are in the situation that we mentioned before, that we are true at the values v1, v2, and vl, and we want to define the general formula. I mean, it's the same idea that we did for 3, but now we just do it in general. So now we just have to be a bit more careful. And so now we define beta sub ij, right? So beta sub ij, because now it depends on two things, because we have the values v sub I, where we want it to be true, but we have various i's. And this one is going to be a sub j or negative a sub j, or not a sub j, depending on the value of v sub I on j. And we're going to get alpha I to be the conjunction of the beta i's, beta I1, beta I2, beta Ik. And finally, we let alpha be the disjunction of alpha 1, alpha 2, all the way up to alpha L. Alright, so we have a disjunction of conjunctions at the end. And that's the formula we had. This formula is true exactly on V1, V2, up to VL. So we get that, yes, we managed to build for each Boolean function a formula that corresponds to it. So that means that the language is complete. So this what we just proved is the completeness of the language for sentential logic. So everything that you might want to say in sentential logic, you can write only with these connectives that we have so far. So that's great. So that means like even if it's just the fact that it's 5 is not restrictive at all. So we can improve this result a little bit, and we can show that every k-place Boolean function not only comes from a well-formed formula, you can show that there is a well-formed formula alpha on the variables a1 up to ak that use only the connectives or and not. Okay, so only with the connectives or and not. That's it. Not and, not even only if, not implies. Only those two connectives. You can write a formula that is going to represent the formula f that you're given. Yeah, so this is quite something. So you can represent all k-place Boolean functions only with and or. You don't need anything else. Here is the proof. So we already know that there is a well-formed formula. Let's call it alpha tilde, whose Boolean function is the f. This alpha tilde might use the connectives and well, in the proof we did before, we only use ands and ors and not. We didn't use anything else. But okay, let's suppose this one uses anything. And what we're gonna do is just replace each occurrence of if and only if inside alpha tilde for this formula. So whenever you see an if and only if, you replace it for this bigger formula. And then we keep on going. So now we have a formula that has no if and only if. Now we replace each occurrence of implication of phi implies psi by not phi or psi, which remember this is equivalent to phi implies psi. So now we just replace each one for this, and now we have a formula that has no implications. So no if and only if and no implications. And now finally we replace each and by not phi or not psi. And now we end up with a formula that has no ands either. We end up with a formula that only has nots and ors and is equivalent to the alpha tilde that we started with, and the alpha tilde that we started with was representing the function that we had. So all functions, all Boolean functions can be represented only with or and ands. Alright, so that's it for today, or it's for this video. See you guys next time.